Hello, everyone. You might recognize me from being around campus at the Planetarium, helping out a lot. I've had a lot of good opportunities here. It's been really awesome to take classes and be working here and doing research here as well. But I've moved on. I'm going to CSULB right now. I'm doing the Astro program over here, and I am very excited to be able to introduce our guest speaker tonight and my current mentor, Dr. Zinn. So let's get started with that. Dr. Zinn received his BA in Astrophysical Sciences from Princeton University, achieving magna cum laude honors, and received his PhD at The Ohio State University. From there, he moved on and went to the University of New South Wales for his postdoctoral appointment, and then a NSF Astronomy and Astrophysics postdoctoral fellowship at the American Museum of Natural History, before finding his way to Cal State Long Beach as an assistant professor of physics and astronomy. His research pertains to asteroseismology and galactic archaeology, utilizing space-based telescopes and surveys such as Gaia, Kepler, K2, and TESS. Along with the multiple projects and teaching at CSULB, Dr. Zinn oversees weekly observation nights, Night of the Observatory. So best combo is to come here to the Planetarium to check out a show and drive 40 minutes to Long Beach to go check out that on Tuesday nights, right? He also hosts a lot of astronomy outreach events, such as the most recent partial solar eclipse that we had. And also, too, on top of it, he also inaugurated the Mobile Planetarium at Long Beach, where we go ahead and take it to high schools in LA County and show high schoolers the wonders of astronomy and physics. With that introduction, and it's a great honor to be able to do this, I'd like to present Dr. Joel Zinn for his presentation on asteroseismology.
Thank you so much, Trevor, for that kind introduction. I'm sorry, but not sorry that I've stolen Trevor away. It's great to have him as a student. And it is a great pleasure to be here today. I'd like to thank the organizers for inviting me. So without further ado, let's get started. So today's topic is close to my heart. It is what I do day in and day out when I'm not teaching or doing outreach, as Trevor said. So we're going to be talking about sound waves and stars. Asteroseismology is a fancy name for it. And I would like to give an overview of the field. So we're going to first start out with the beginnings of the field, some basics about what asteroseismology is, and then move into some flashy results that have come through the years. So we're going to be taking a look at these greatest hits of asteroseismology through the decades. I don't know if anyone in the audience has listened to Kids Bop, but anyway, that was the 2000s for me. So we're going to do the Kids Pop version of asteroseismology today. The history of asteroseismology starts actually in Southern California at the Mount Wilson Observatory, which was known back in the day as Mount Wilson Solar Observatory. And we're going to be talking about some important results from that time on magnetic fields and the quote, 5-minute solar oscillations, which will become important in the story of asteroseismology. And then we're going to go into what I'm calling the middle years. We're going to focus on Big Bear Solar Observatory, which has been important for the results pertaining to the solar abundance problem and determining the inner rotation profile of the sun. And then finally, we're going to upgrade to today to space-based asteroseismology. I don't know what is on Kids Bop 2024, but I'm intrigued. And we're going to be talking about Kepler and TESS. You may have heard of Kepler and TESS. These are space-based missions that are doing asteroseismology. And it's doing really interesting work. There are very interesting results about red giant stars. We'll get into what that means in a little bit. So the story begins, I would say, in many ways with George Hale. George Hale founded Mount Wilson Observatory, Mount Wilson Solar Observatory, in 1904. And this is a picture of him in front of a spectrograph. He also helped found Caltech, for what it's worth. So the origins of asteroseismology are rooted in Southern California. He had the idea of creating a world-class solar observatory, and we see that here. This is the 60-foot tower that houses a lens at the top to focus light. from the sun, and this is a solar observatory. Now, looking at this, you might recognize the structure. It looks a little familiar. It's actually adapted from a water tower. And the way it works is you have light coming here, it's collimated down into this tube, and that goes actually underground into a subterranean spectrograph, which is about 30 feet. And you may ask why we would build a telescope on a tower, or why Hale would have this idea to build a telescope on a tower. And it has to do with trying to avoid heat that the lens would absorb from the sun if it were closer to the ground. Of course, these lenses back in the day were formed of glass, and so they would expand as they heated up. That would be bad for the optics. So the idea here would be to get it off the ground as far as you could, and therefore reduce any blurring that you would get from this expansion of the lens. So this went up in 1908, and it underwent some modifications since then. It first got upgraded to quartz, a quartz lens, actually Pyrex first. You of course know Pyrex because it is durable and you can put it in the oven because it has a low thermal coefficient of expansion. So that made it good for this problem, and then later it was moved to quartz in the 1960s. So we'll get to the 1960s in a little bit, but I want to zoom in on what the spectrograph actually is. I said it's this 30-foot thing, but we all know what a spectrograph is. It's basically a prism. So in, I guess, elementary school, we played with prisms. You pass white light, which has all colors of light in it. Through a prism, it will refract that light, and you will be able to separate out the different colors of light. So red being the longest wavelength of light, and blue being the shortest wavelength that we can see with our eyes. Okay? So that's essentially what that spectroscope did in the subterranean lab. And what you would get, you may have also seen, is a solar spectrum. So the solar spectrum looks like a rainbow, except it has certain wavelengths taken out. Okay? And this has been known for some time, first discovered by a chemist in the early 1800s, that there are lines in the solar spectrum. These lines correspond to different absorption wavelengths of certain kind of atoms. So depending on how strong these wavelengths are, how strong the absorption that is, you can determine how much of a certain element is in the sun. Right? So here are some absorption lines, and what Hale did was to take advantage of this, this spectrograph to take spectra of the sun. So here we have a picture from Hale's 1908 paper, which ended up being very important, showing the surface of the sun, and you have some sunspots here. So his idea was to take some solar spectra with this 60-foot tower, and he looked at the spectra in two different regions, one with a sunspot, as you can see here, and one without, and plotted their spectra there. What you can see is that there's a wavelength that is singled out, this 5436.80. In the top spectrum from the non-solar spot, you see that it's just one line. Okay, there's just one kind of line there. And then in the solar sunspot spectrum, it actually bifurcates into two, which is not as clear in this picture. They were dealing with images taken on spectrographic plates, so they weren't always the best quality, but we can zoom in a little bit and see that there are indeed two lines down there. So if I flash this, there's a hint of that there, right? What Hale saw here was not new. In fact, the splitting of lines had been seen before in 1892 at Princeton, so I've got to give the Princeton plug there. But Hale is really credited with a big discovery in this case because he connected the dots. He said, okay, there's a split line. I also know from laboratory experiments that if you take a spectrum of a gas that is in a high magnetic field, the lines will split. So maybe these sunspots actually have strong magnetic fields. And so this was the first detection of a magnetic field outside of the Earth. And it was on the sun. So this is sort of what the sun looks like, right? It's basically a bar magnet, as it turns out. We've seen bar magnets before. Again, maybe in primary school. If you take iron filings, you can put them near the magnet and they'll trace out field lines. So there's a north pole, there's a south pole, and the strength of the magnetic field is proportional to the density of those lines. So the magnetic field is stronger toward the poles. It also represents the direction that particles will tend to travel along these field lines. Sorry for the audio here. Some beats, some Kids Bop beats. Okay, so this is what the sun's magnetic field looks like with modern instrumentation. You do basically the same thing, take spectra of every part of the sun, and you can determine how much magnetic field any part has. The magnetic fields are now colored by their polarity. So the north poles are one color and the south poles are another. I don't know which they are actually here. So the darker regions are one polarity and the white regions are another. You can see that they are connected by field lines, right? And there's also a larger magnetic field that envelops the whole sun. And that's the larger, it's called a poloidal magnetic field. That's the kind of bar magnet structure where you have that looping that goes on. So, the sun is a very dynamic place. And these magnetic fields can be very strong. So usually the sun, its surface has a field strength of something like a few Gauss. For reference here on the Earth, the magnetic field is something like 0.3 Gauss. But in these sunspots, they can be a few thousand Gauss. So that's incidentally what causes sunspots to appear like sunspots. The magnetic fields rob energy from the gas, and so that gas is cooler, and therefore doesn't shine as much as the rest of the sun. All right, I'd like to, at this point, quote this person, Robert Layton, who said, if the sun didn't have a magnetic field, then it would be as boring a star as most astronomers think it is. That's because, well, I interpret this statement to say, astronomers ignore magnetic fields a lot because they can be very complicated. As you saw, it has a weird topology. It's sort of messy. And I quote Robert Layton because actually Robert Layton is the next crucial person in this journey of asteroseismology. He is really the founder of asteroseismology. Hale did a lot of the groundwork, built this observatory, Mount Wilson Solar Observatory, as it was known for the first 15 years, until the 100-inch telescope was installed, which Hubble made his big discovery on. But Hale may have set the stage. Robert Layton really took that instrument and did a lot of interesting work to found the field of asteroseismology. So he, again, looked at solar spectra. And if you take a look at this solar spectrum, you can zoom into these lines here. And we're going to plot this in a different way. We're going to now make a plot out of this picture. So now the y-axis here is how much light you're receiving from any point in the spectrum. So as you go along, when you have dips, that corresponds to an absorption line. And plotted here in vertical lines are the absorption lines as they would be measured in the lab. So if you just had a bit of gas and took its spectrum, you would see the lines exist there. Okay? That's if the gas is not moving with respect to you. But as it turns out, light is subject to a Doppler effect, such that if you have the gas moving, for instance, if the solar surface is moving, you're going to redshift and blue shift that absorption line. So when the surface of the sun, for instance, is moving toward us, the absorption line is going to be blue shifted. When it's moving away from us, the absorption line is going to be redshifted. In other words, moved to redder, longer wavelengths. So this can give us maps of the velocity of the surface of the sun. The higher the velocity, the stronger this redshift or blue shift effect is. And we all know the Doppler effect because you hear a siren as it's coming toward you at a higher frequency than when it's going away from you. It's the exact same principle, except with light. So, Layton took images of the sun that would otherwise be projected onto a photographic plate. This is obviously a modern image of the sun for what it's worth from Big Bear Solar Observatory. We'll talk about that in a little bit. But what he did is he then took a slit, passed that light through a spectrum, and every point in this slit would get a spectrum. So this part of the sun would get a little spectrum, this part of the sun would get a spectrum, and in general, the solar surface is going to be moving up and down at different rates at different places on the surface. So he could look at these absorption lines, see how much they've been redshifted or blue shifted, and then make an image of the sun showing the velocity field of the sun. So that's what we're going to see now, is he took a mechanical arm and moved this slit across the image of the sun, and as he did so, he would build up this velocity map. It's called a Dopplergram. Okay. So this map is now showing regions of the sun that are moving toward us, and regions of the sun that are moving away from us, that are colored white and black, with the intensity of the white or black corresponding to how fast the sun is moving toward or away from us. So you can see there's a large scale feature. That's due to the rotation of the sun. We'll talk about the rotation of the sun, don't worry, but it is rotating. So at any given time, part of the sun is moving toward us and part is moving away from us. But then there are also these smaller scale variations that we'll also talk about. Okay, so this is Robert Leighton pictured with one of his Dopplergrams. And he did this work in 1962. So this was around the time when the lens was upgraded to have this quartz lens and was producing all these great images. But he didn't stop there. He said, okay, I can take these Dopplergrams and actually make two of them, one after the other. So we start off with a picture of the sun, and we're going to make the first image. You would put a photographic plate down, get your Dopplergram going. And now you see that this is now going to be an image of the velocity field as a function of time across the surface of the sun. Now, what he did is, at this point, he would quickly change out the photographic plates within a few seconds and put a new one in to make a second image, now moving the other way back across the surface of the sun. So now we have two Dopplergrams, and you would imagine that if we take a look at the right-hand side of both of these Dopplergrams, we would see that they look about the same, since they were taken basically one after the other. The velocity field is not going to change that much in a few seconds, in the time that it took Leighton to change out his photographic plates. The regions in the middle of these two plates will be different from each other, because the velocity field will decohere, it'll just kind of do its own thing. It's not going to be doing the same thing that it was, 30 seconds ago, let's say. And even more so for the left-hand side of these images. They're going to be very different. That was a prediction, or a prediction. But this is not what Leighton saw. So this is now that, what he did was he took a difference of these two images and plotted it up like this. We're going to flip it around like the plot that he actually made. So now the right-hand side that we were looking at is now on the left-hand side. And he's plotting what the time difference is between the two plates. So you would imagine, as we said, that the right-hand sides of those plates would look very similar. So when you subtract them, they'll tend to make a smooth grayscale image. And that's what's being shown in this part of the strip, right? All across that part of the sun, it's sort of smooth. 150 seconds in the middle of the image, when you take the two images and subtract them from each other, you would expect to get something that looks pretty different. And indeed, you see pretty much white noise there. So little bits of the surface of the sun are doing different things. And then you would have expected that this other side would also look different, perhaps even more different, but that's not what you see. You see that it looks sort of like at zero time. It looks a little grayscale smoother. So 300 seconds, this time difference, as it happens, corresponds to about 5 minutes. These ended up being known as the 5-minute solar oscillations. What this is saying is that the velocity field of the sun repeats itself about every 5 minutes. So it's bobbing up and down in some way every 5 minutes. It's oscillating. So this was a groundbreaking discovery and really set the stage for asteroseismology. And I keep on saying this word asteroseismology, so I want to explain a little more about how asteroseismology works and what it is. But the point is that we're going to try to get at why these 5-minute solar oscillations exist. Okay? And in some ways, that's the heart of what asteroseismology is. So to begin unraveling this mystery of the 5-minute solar oscillations, I'm going to show you a picture of the Princeton University Chapel, where I spent a lot of time. Let me see if I can get that picture back. Yeah. Well, it's not going to stay there for long. But on the sides, you see organ pipes, right? I sang in the chapel choir there and also worked at the chapel. So I spent a lot of time at the chapel and was privy to listening to this beautiful organ a lot. And I'm going to tell you that the sun is like an organ. So we're going to actually talk a little bit about organs. Now this is the beautiful Princeton University organ playing here. Okay. So we'll come back to this in a little bit, but let's go through exactly how organs work. Okay. Organ pipes can come in a couple of varieties. You can have a reed pipe, which looks like a clarinet, basically, inverted clarinet, where you have a reed at the bottom. You pass air through it from vents that you control with the keyboard and your pedals, and that will induce some pressure variations in the air at the bottom of the pipe. Those pressure variations then find their way out through an open hole at the top. Okay. You can also have a flute pipe, which operates under a similar principle. When you pass air over this, this lip, it will create variations in the pressure that then travel up the tube. Okay. And it's like a flute, right? Just a big flute. So the biggest organ pipe at the Princeton University Chapel is something like 32 feet. And you can get a variety of sounds that come out of a big pipe versus a small pipe. Now, this is a sort of model of what an organ pipe looks like, according to a physicist. So it's just a pipe that's closed on one end and open on the other. And what we're doing when we excite the sound in an organ pipe is we send pressure variations at the bottom of the pipe, then travel up the top of the pipe. So this is a video from the acoustics lab at University of New South Wales. Trevor said that I did a postdoc there, had a great time. I didn't get to do any research with them at the acoustics lab, but they're very cool. They have a lot of great pedagogical materials online, so highly recommend checking them out if you're at all interested in the physics of sound, which, as we'll see, why I de facto am, even though I study stars. So we're going to imagine that we send up a little pulse of high pressure air from the bottom of the pipe up to the top. And we're just going to follow and see what it does. So we're going to turn on time here. And what this animation is showing, I'll narrate it as it repeats, is this high density or a high pressure pulse travels from the top of the pipe. As it leaves the pipe, it leaves behind a little wake that becomes a vacuum that will, like you do when you use a straw, suck up gas from the bottom. When you suck up gas from the bottom, you can think of that actually as a little vacuum pulse that travels down the pipe. Okay? That vacuum pulse, when it gets to the bottom of the pipe, doesn't have anything more to suck on at the bottom, so it's just going to rebound back up. As that vacuum is going to rebound back up here. There's a little bit of a mismatch when it repeats, but there you go, there it is. When it got to the top, that vacuum will then allow air from the outside to come in and induce a high pressure pulse that'll then come back down and repeat the process. Okay? It'll bounce at the bottom and come back up. So as soon as you send a pulse like this, it will tend to establish what are called standing waves that occur at a particular frequency that depends on the length of the pipe. So the frequency of sound that we would hear from this note that the pipe is sounding would be, of course, the number of times that we would get a high pressure pulse coming to our ear. Now, this is obviously slowed down a whole lot. The sort of oscillations that we hear, the sound waves that we hear with our ears, are of order 100 pulses per second, okay, in the hundreds of hertz range. So the key point here is that the frequency that this pipe will make depends on a couple of things. One is an obvious thing, that it'll depend on the length of the pipe. If you were to lengthen this pipe, then the pulses would take longer to get from the top to the bottom and back to our ear again. It also will depend on the speed of sound, which is effectively what we've slowed down in this animation. Now, the speed of light or speed of sound in air at the surface of the Earth is something like 350 meters per second. And so that's fixed. So in practice, the way that we make different sounds on the organ is to make pipes of different length. Okay. Now, just like we did with the solar spectrum, we can make a plot version of this. We love a plot. This is now showing in blue what the variation in the pressure is at any point along the pipe. So this is the closed end of the pipe. This is the open end of the pipe. All right. So I'm going to turn on time, and we're going to see that this pressure variation changes. The crucial thing that I want you to note is that the pressure variation changes most at the open end of the pipe. As we saw in that video, that's the end of the pipe that sees the high pressure sound wave coming out and the low pressure sound wave going in, right? Now, at the center of the pipe, let me just play this again. At the center of the pipe, because you can't pull or push any gas at the center, there is actually going to be no pressure variation at the very bottom end of the pipe. And that's what's shown here. Okay? So that's the only condition to establish a sound wave in the pipe. The pressure variations have to be big at the top and small at the bottom. Now, in this particular case, we can imagine that this is playing a note, middle C. You can hear that. If we build a pipe of a certain length, okay, it will create that note. Now, when we play a middle C on the organ, we are not just playing middle C, as it turns out, because imagine when you're blowing the air across the reed, into the reed or across the mouth lip, what you will do is, in general, you will send pulses of different frequencies, many different frequencies through the organ pipe. Only some of them will be at this particular frequency. Others may be at a higher frequency. If you get a certain kind of pulse pattern going that is at 3 times that frequency, you can establish a different kind of sound wave, standing wave, that looks like this. Again, it's open at the top, so you have those high pressure variations at the top, and there's no pressure variation at the bottom. Okay? So, and you would hear the sound as like this. So even as you play the middle C on an organ, you are also at the same time playing this other note, and indeed many other notes above that. This is what gives the timbre to a particular instrument, in this case an organ, is these overtones. If you're a musician, that's what they're known as. So we're going to listen to the Princeton University Chapel organ again. This is Trumpet Tune in C by David Johnson, as played at the Princeton University Chapel. And in a moment, we are going to hear that middle C. And it's not going to sound like those very generic tones that I just played. And it's going to come up here. That's the middle C, right? And it doesn't sound like that tone that I just played, because it's playing middle C, but also playing all these overtone notes at the same time. All right. Now you can, again, plottify this, which we love to do. And so this is showing how strong any particular frequency that the instrument supports is. Okay, so as a function of frequency, the larger this curve is, the more sound you would hear at that particular frequency. All right, so this is the note that was quote-unquote played on this clarinet. In this case, it's the spectrum of a clarinet. As we've seen, a clarinet is basically an organ pipe. And you also excite so for references, middle C at a particular frequency here. But you also excite at the same time all these other overtones. Look at all those frequencies that you're playing when you're playing just one note on the clarinet. That's what gives it its characteristic sound or timbre. Okay, what does this all have to do with asteroseismology? You're sitting there like, I didn't come here for a talk on music. The sun is a 3D, spherical, sort of inverted version of an organ pipe. So it's obviously, this is not a 3D picture of the sun, but use your imagination. The outside of the sun is the open part of the pipe. Okay, that's where you can have those large pressure variations, and the center of the sun, you would have no pressure variations. Okay. Except it's a little bit inverted, because instead of exciting the wave at the bottom in the inside of the sun, what happens with the sun is you excite the wave at the top. So this is a video of the surface of the sun showing granulations. So I've denoted this convective envelope. This convective envelope is where the energy is transported in the sun using parcels of gas, hot gas that rise to the top. As they rise to the top, you see them come to the top, they cool off, and then they fall back down. And these characteristic granule sizes are something like the size of Texas. So, yeah, everything's bigger in Texas, but it's bigger on the sun. Or the same size on the sun, I guess. All right, so these convective motions, the point is they will move the gas and create pressure variations that then will travel through the sun. So we can have a little ringing that starts at the surface of the sun and creates a wave that travels to the center and then comes back out. Okay. So this is how sound waves work in the sun. Now, obviously the sun is bigger than an organ pipe, and so the frequencies that it supports are much lower. So instead of having hundreds of pulsations per second, it has one pulsation, turns out, every 5 minutes. So this is the origin of the 5-minute solar oscillations. They're sound waves that travel through the sun like an organ pipe. These sound waves will then generate velocity field variations on the surface. They generate temperature variations on the surface, and we're able to, in effect, see the sound of the sun. So this 5-minute solar oscillation depends, of course, on the size of the sun, but that's not the only thing it depends on. As I said, you can change the frequency of the sound that you get from an instrument by changing the sound speed. So the sound speed of the sun is not constant as you go inside the sun. So we're going to start off from the surface of the sun and move inward. As we do, the sound speed is going to increase. Here I'm going to put an image from Layton's paper of the sun. And it's only about halfway through the sun that we get to the sound speeds that we're familiar with on the Earth. So this means effectively that most of these sound waves spend most of their time traveling near the surface of the sun because they're just really going at a snail's pace. And this sound speed, in part, coupled with the size of the sun, gives us what frequencies the sun will support. Okay? And this is important because if we can then measure the frequencies of the sun, we can determine the sound speed that's inside the sun. So I'm going to now show you what a solar spectrum looks like. We've seen the clarinet spectrum. This is now what the solar spectrum looks like, where we have frequencies here in a weird unit on the x-axis. A microhertz is 1/1,000,000th of a hertz. So instead of hundreds of hertz, it's much, much lower because the sun is much, much bigger. And again, it's proportional to how much power is emitted at a particular frequency. In this case, we are measuring that power in velocity variations, just like Layton did. We'll get into how that's measured in a little bit. But each one of these modes, if you zoom in on them, has a particular frequency. Now they're all at about 5 minutes. That's about the period of these waves. But they do have in detail different frequencies. And each one of these frequencies corresponds to a different standing wave pattern. So with the organ, we saw that the standing wave looks like something like a sine wave. That's because an organ pipe, at least to physicists, is a 1D thing. The sun, as I've said, is a 3D thing. And I'm not showing you quite a 3D thing here, but I'm showing you a 2D standing wave. That's what these pictures here are. And the colors here we can take to represent, for instance, the velocity of the surface of the sun. So the blue are regions that are traveling toward us. That's blue shifting the light. And the red are the parts traveling away from us. So at any given time, the sun is oscillating in all of these different sound waves. It's supporting all of these different acoustics. Okay? All of these different overtones. Such that when you add them all together, what you get is something that varies in a 3D funky looking way. Now this is not showing all the small scale behavior on small spatial scales, but it is getting you some estimate about what the larger scale behavior that we can see on the sun looks like. And this is what it looks like. If you were to make an audio version of this, it would sound something like this. We're going to hear one mode, one standing wave pattern on the sun right now. We're going to hear another one, and then another one, and then them together. So this is the second one, higher frequency. That's an overtone. And it's been scaled up so we can hear it. Okay, that's the third one, and then all together in a little bit. So that's only with 3 modes. There are about 10 to the 7 modes that exist in the sun. So it wouldn't sound necessarily very nice. And we played them all together. Okay, so how do we measure this solar spectrum? I showed you it, but I didn't tell you how we got it. Layton got the rough picture. He got that they're all of order 5 minutes. But what he was seeing was actually the accumulation of all the different modes that are excited on the sun. But when we want to make a spectrum and separate them out like that, we need to have pretty good data. And Big Bear Solar Observatory is helping us do that. Founded in 1969 on Big Bear Lake, built by Caltech. It's now operated by New Jersey Institute of Technology since 1997. The point is that it's great, one of the best sites in the world for solar observing. Why is that? It's not built on a tower, you see, so what's making it so good? It's that it's on a lake. So the lake will absorb the energy from the sun, making the air not absorb as much heat. So it regulates temperature in a similar way that the 60-foot tower would regulate the temperature of the telescope there. So you would like to continuously monitor the sun to see those sound waves as a function of years at all times. Big Bear can't do it on its own because it does experience nighttime like every other place on the Earth. So to actually get great data, we need to establish a network of these nodes. This is called the GOM network. So Big Bear is just a part of this larger network of telescopes observing the sun. This is a picture that Big Bear took this week. I think you could go online right now. Don't do it right now, but later. And download an image of the sun for your very own, put it on your screensaver or whatever you want to do with it. And this is much better data than we were getting from Leighton's work on Mount Wilson Observatory. It's very crisp, clear, very beautiful data. You can also take a Dopplergram. Also looks pretty cool. A better version of Leighton's work. Okay. So that ultimately is how we get the solar spectrum, is we take Dopplergrams, basically, to this day. Just better versions with better time resolution and stuff. Okay. So I'm going to now transition into talking a little bit about some of the results that come out of asteroseismology. And I'm going to begin with the solar abundance problem. So what is the sun made out of? That is a question that one might ask. And one has been asking that question, or some people have, for many years. Lord Kelvin in 1862 thought that the sun was of meteoritic composition, so made of the same stuff as meteorites. That, as it turns out, was not a bad guess. Sir Arthur Eddington later on wrote the book on the sun in 1926, and it was called The Internal Constitution of the Stars, which is quite an interesting name. It dates it, I would say, of the stars, of the Facebook. In discussing, he says in discussing numerical results, we have in mind as the most likely constitution of the material a predominance of elements in the neighborhood of iron with some admixture of lighter non-metallic elements, which is 1926 speak, scientific speak at that, for saying that he thought everything in the sun was mostly stuff like iron, cobalt, nickel. And that is how the field stood at 1926. The person who wrote the book on the sun thought that. Until Cecilia Payne-Kapuskin wrote her PhD thesis in I think it was published in 1925. And in this PhD thesis, she completely overturned the idea of what the sun was made out of. And for this work, she got the first PhD in astronomy from Harvard. What she said in this work called Stellar Atmospheres, a contribution to the observational study of high temperature in the reversing layers of stars, which I wish I could say is 1926 speak, but that's really just scientific speak, I guess. She said that the sun was mostly made out of hydrogen and helium. She has this table here, which is really bearing the lead, but this column is showing how much of the particular element there is. How she got this was she looked at spectra of the sun. As I hinted at before, if you can measure how deep an absorption line is, you can determine how much of a particular element there is. So if we look here at hydrogen, it's at 11. Now, what does that mean? Crank it up to 11. This is in a logarithmic scale. So compared to, for instance, magnesium at 5.6, hydrogen is about 100,000 times more abundant in the solar atmosphere. So the vast majority of stuff she thought was in hydrogen and helium. And she ended up being right. This is what we think today is the relative abundance of all the elements in the sun. This is showing, again, the abundance in log scale. So hydrogen is at 12, not far off from her 11. And everything else can't compare. So hydrogen and then helium, the next most abundant element is oxygen, as it turns out. And oxygen is many times, 100 times less abundant than hydrogen in the sun. So you can determine abundances of things from looking at stellar spectra. You can also determine abundances by looking at meteorites. So this is a picture of the Wilmette meteorite from the American Museum of Natural History, where I was as a postdoc. And you can measure how much of every element there is in meteorites. There's a whole big department to do similar sort of studies with these samples at the museum. And that's a lot of how you get at the abundance values for instance, these iron elements like iron, nickel, chromium around here. A lot of the heavier elements you can get from the meteorites. That's because the sun and meteorites were formed from the same stuff initially. But you can't do that with some of the lighter elements, or at least it's harder. It is harder for oxygen, because oxygen has a lower condensation temperature, which means that it was harder to make into rocks at the early beginning of the solar system, so it didn't end up as much in meteorites. That's where you have to go to stellar atmospheres to do that. But in general, you can compare what you get if you study the spectrum of the sun from looking at meteorites, and you can subtract the abundance that you get from one method versus the other. If they completely agreed, all of these elements would be at zero. Looks pretty good, What is missing here, though, is oxygen. This is from 1998. At the time, the oxygen was not as reliable. Since then, there have been measurements of oxygen in meteorites, and you can look at that. But I'm going to tell you a secret, that the photospheric abundance of oxygen changed in 2005. So people updated their models and found that oxygen seems to be less abundant by a factor of 2 than in this 1998 paper. So the third most common element, we didn't know by a factor of 2. That's pretty scary. And so in asteroseismology, I told you the asteroseismology is sensitive to the sound wave, sound speed inside the sun. It turns out, what else is the sound speed in the sun sensitive to? It is sensitive to the composition, what the gas is made out of. So depending on how much oxygen you put in, you will get out a different sound speed. And you can subtract that sound speed from the sound speed that you infer from asteroseismology. And so this was the 2005 updated, quote-unquote, updated modern value of the oxygen. It does not look as good as the 1998 version, right? This 1998 version is closer to the 0 line. I think we can all agree. And this, I think, really hit home the fact that just because it's newer doesn't mean it's better. People are still debating about how much oxygen there is, but in my heart of hearts, as an astroseismologist, I say it's not a factor too low. So that's the solar abundance problem solved from asteroseismology. And that's not the only thing that asteroseismology can do for us. You can also look at the rotation of the sun. Turns out that the sound waves are sensitive to rotation, and I'm going to tell us why. This is the rotation of the sun. It is spinning once every about 25 days. And this we can determine based on just looking at the surface of the sun. We can track sunspots as they go along the sun and determine what the rotation profile is at the surface of the sun. But that's not the only way you can do this, and you can do a little bit more, in fact, a lot more with asteroseismology. Here's how you do that. These are standing waves that can be supported in the sun. This middle one would oscillate like this. Again, the blue regions could represent parts of the star that are moving toward us, red regions away from us. And we're going to take now a look at these modes on the side here. One of these, actually, it turns out standing waves can rotate. So this one is rotating that direction, and the other one on the other side is rotating in the opposite direction. Now, if you were to zoom into one of these regions of the sun, you would find that the oscillation is all 5 minutes, no matter which mode you look at. It's going to be 5 minutes. And in fact, it's going to be the exact same frequency. For all of these sound waves, they're going to have the exact same frequency. However, this will not be true as soon as you add rotation to the sun. Okay? So the mode that is going to be traveling in the direction of the sun, this one, is going to be Doppler boosted. Again, the Doppler effect. So the frequency of that one is actually going to be higher than the frequency of this one. So if you were to measure the oscillations at this part in the sun, this one would be lower than this one, and this one would be in between the two. So we can model that. This is now zoomed into one of those frequencies that we saw in the spectrum. And what I'm going to do is just show what happens when you allow the sun to rotate. those frequencies are going to be split. Whereas they were exactly equal before, as soon as you allow the sun to rotate, they're going to be split. The amount of splitting is proportional to how fast the sun is rotating. So you may say, well, we can just look at the sun and see how fast it's rotating. But that's only the rotation rate at the surface of the sun. These modes actually are 3D modes. I've not shown them in 3D except in that one GIF. But they are sensitive to the rotation rate as a function of depth in the sun, as it turns out, and not just the surface. So you can make this beautiful plot here, which is showing what is called differential rotation. What we have here is a rotation rate on the y-axis. Faster spinning is higher up here. And this is going from the sun's surface to the core. It stops about halfway because it turns out asteroseismic modes can't penetrate all the way to the interior of the sun. And each one of these curves is a different latitude. So we're following lines of constant latitude. You just send a laser in. At the equator, that would be the 0 line. You would find that the solar rotation rate decreases as you go down. And it increases if you send a laser from closer to the pole. The point is that these curves are not the same. So the sun is actually not rotating at the same rate at every latitude on the sun. So this is another way of viewing it, where the color here is proportional to how fast the sun is rotating. And this is the equator, and this is the pole, and this is kind of like a cross section. So you can see that the poles are not rotating as fast as the equator. This is a picture based on gong data. So the Big Bear Solar Observatory contributed to this data and allowed us to see peek inside the sun, essentially. It's the only way, asteroseismology, well, mostly the only way to peek inside the sun. You can also do some neutrino physics. But there you go. So why is the differential rotation interesting? Why is it important? It goes back to Hale's work, as it turns out, because this is how a magnetic field is generated in the sun in the first place, to generate those sunspots. What you do is you start off with that colloidal field line structure, where you have a bar magnet up and down. You then apply this differential rotation in the sun. The equators are going to be spinning faster. The magnetic field tends to couple to the gas. So if the gas is moving around, the magnetic field lines are also going to move around. And that will generate these toroidal field lines, which are horizontal looking. All right, what's the big deal about these horizontal field lines? Well, it turns out there's one more step in this. So down here, you take those horizontal field lines. Convection, which we've also talked about, the convective envelope is where you have hot gas coming to the top, and you have granules at the surface. As they come up, they're going to actually twist in the same way that hurricanes rotate in different directions in the northern and southern hemispheres of the Earth. That same Coriolis effect is responsible for twisting of the convective granules, and therefore for twisting of these magnetic field lines. They tend to twist in these loops that then can add constructively, and you get, again, a colloidal field. So you've gone from one colloidal field to more colloidal fields, and this is how you generate a magnetic field. It's called the dynamo mechanism, and this is how we think magnetic fields are generated in the sun. Now, to predict how much of a magnetic field would be generated in the sun, you need to know the differential profile as a function of depth in the sun, which you can only get from, for instance, gong data, asteroseismic data. All right. So this is what a model would predict for the magnetic field of the sun during a solar eclipse. I think this was a solar eclipse in 2008. So this is a model. You see the magnetic field lines. You can also make a model of how bright the corona would be. I hope many of us saw the eclipse, if not in totality, in partial eclipse here from Southern California. And this is the actual picture of what the corona looked like during the total solar eclipse. So we're able to model the magnetic field of the sun pretty well. And this is also another kind of picture of what the corona is up to. You have, this is basically the sun being blocked out, and you have emission from the surface of the sun. Okay, so I've talked about the sun now. I want to move on to talk about other stars. And this is where we're going to get into the space-based era. So we talked about gong. With gong data, you can determine the composition of the sun, how much oxygen there is with that debate, and also the internal profile of the sun. But we're not just interested in the sun, we're also interested in other stars, or at least I am, and therefore you are tonight. So this is the evolution of what the sun looks like. For a solar mass star, you start off as a big ball of gas, it collapses into a disk, and then at the middle collapses into a star. That's a whole other talk. And we're not going to get into that today, but you form a main sequence star, like the sun we have today. Yellow-looking thing, we all love it. It will then evolve and get bigger. In 4.5 billion years, it will puff up and become what's known as a red giant. So, what does this look like? It looks like this. Start off with the sun, and then you get much bigger. Up to 100 times the size of the sun. That's how it is now. That's how big it will be. And because they're so big, their frequencies are going to be much lower. These stars are going to ring at different frequencies than the sun will. It turns out that they oscillate at low enough frequencies to do pretty well with space-based observatories that were designed to look for planets, mostly, like Kepler. So Kepler, as it happens, has observed the asteroseismic frequencies of a lot of red giants in the galaxy. So it looked along the ecliptic, which is the plane in which all the planets rotate. It also looked in a different field that was pointed toward the Cygnus constellation. That's the Kepler field there in gray. And these are all red giants that have been observed with Kepler and its subsequent version using the same instrument called K2. Right. Now this is very exciting for someone like me who studies red giants and using asteroseismology. And I want to take you through a couple of the high notes from the space-based era of asteroseismology. Kepler, for reference, was launched in 2009 and observed for about 4 years. And as it did so, it took a lot of great asteroseismic data. So we're going to come back to this rotation thing. If this is the rotation of the sun, as it is now, it's not going to remain that way when it becomes a red giant. Why is that? Because it's getting bigger. So just like a ice skater, when they pull their arms in, will rotate up. If they were to let their arms out, they would spin down. In a similar way, if the sun goes to be a big red giant, it's going to spin down. That's the conservation of angular momentum. And what this looks like is something like this. Even though, in general, the star is going to get bigger, it turns out that the radiative core is going to shrink. All right. So it's at once getting bigger and smaller at the same time, which I hope to show you in this animation. So the outside is getting bigger, that's what we see, but the inside is getting smaller. That's what we can't see, at least without asteroseismology. What we would predict is, according to the ice skater analogy, this core should spin up as it gets smaller. And indeed, that is what was found. So in 2012, the Kepler satellite, as pictured here, is looking very happy with this result. These authors, de Heuvel's et al., found a star that seemed to have a spinning core. So it can be tricky to do, but it turns out you can, for these giant stars, in a way that you can't with the sun, actually be sensitive to the rotation of the core. Remember that plot of the, well, we'll see it in a second, the plot of the sun's rotation profile didn't go down to the core. For these giants, you can go pretty deep. And you can do that based on these splittings. So this is similar to the splitting that we saw in that animation before, where these would, without the rotation of the star, be just at one frequency, but instead they've been split into two. And this, although it's not obvious, here too you have 3 peaks, right, like in the animation that we saw. Although it's not obvious, this is a telltale sign of rotation in the core. And you can make a rotation profile for this red giant, which is what they did. So this is what we've seen before for the sun. And now this is what they got for this red giant. And as you can see, it does go down from the surface all the way down to the core in a way that the solar profile doesn't. And what you see is that it may be spinning slowly at the top, right? It's at lower rotation rate, but it's faster in the center. Okay, this was all very interesting, and the first time that such a thing had been found. Now, I told you that the core would spin up as it shrank. I lied to you a little bit. It will, but it will be counteracted, we think, by other things going on. In particular, there's this thing called the Taylor-Spruitt dynamo loop, which is a way to generate a small magnetic field in the core of one of these giants. And it turns out that that magnetic field can spin down the core. So how it works in the first place is you have, again, differential rotation. We see that that differential rotation will convert a colloidal field into a toroidal field. Okay. As it does so, those loops of toroidal field lines won't want to stack on top of each other very well. So it's sort of like a herniated disc situation where you'll have jutting out of those discs, and they'll sort of tend to, some of them will jumble together to make another poloidal field. And that way you'll generate a little magnetic field. The importance of this is that you can have a magnetic field in the center of these stars that will tend to, as it turns out, slow down the spinning of the core. It couples with the gas in the interior of the star, and it will tend to tug on the gas outside of it, slowing it down a little bit. So Taylor was the one who came up with this mechanism, and in his paper describing this in 1972, said the following: having indicated that the results may not be immediately applicable to any real stars, we now move on, basically. So he thought that this would never be seen, but there is evidence for this in these red giants. Okay, the Taylor super dynamo loop seems to be active in these giants, and I'll show you why now. Now, I recognize this is a busy plot. I apologize for that. We're gonna step through it. So this is the radius of the star that you're looking at. Okay, each one of these points is a measurement of the core rotation rate of a giant. So you started off in 2012, which is just one. So that was then. This is now. And this is in a paper from 2014. So since then, between 2012 and 2014, we've added all these stars, where we could measure the core rotation rate using Kepler data from asteroseismology, another plug. What we see, well, what we'd expect to see maybe naively is a thing that looks like this. So the rotation rate is now in the different direction. So things are moving faster the lower you are on this plot, and moving slower the further up you are. Again, I apologize. So you would expect from this conservation of angular momentum that the core will decrease with as the star spins up, or it gets bigger. So each one of these giants is essentially like a snapshot of what the sun would be in the future as it evolves. So as we go from left to right, this is the future of the sun, essentially. And that's not what we see. The data are here, not here. All right, that's a big takeaway. This Taylor spirit dynamo can slow down the core a little bit, but the point is that the cores of these red giants are much slower, even than we expected with the slowing down of magnetic fields. So this is still a mystery why the cores of these magnetic fields are so slowly spinning. So watch this space, I guess. Okay, another really interesting result that's come out of asteroseismology from Kepler is the following, and it might not look interesting at first, but I'm going to tell you why it is. This is a spectrum, a zoom in of a spectrum with two stars. You've seen these spectra before, we know that we love them. This is now colored by the exact standing wave pattern that each of these frequencies corresponds to. And for reference, I put for visual reference what these dipole modes in red, L equals 1, would look like. They would look something like this. You'd have half the star doing one thing, half the star doing the other thing at any given time. Again, that's those 2D, really read 3D standing waves. Okay, this is with one star. This is a twin of that star that is essentially the same in every way. Its spectrum looks the same, it has the same frequencies here, except that the dipole modes have a much lower amplitude. They're not as strong. It's not producing as much power at the surface as we would expect. This is a bit of a mystery, or it was when it was discovered in 2016 by my postdoc mentor, Dennis Stello, at the University of New South Wales. If you look at all the stars in Kepler, you will find that up to 50% of stars have this dipole suppressed pattern. So it tends to be these more massive stars. If you look below about 1 solar mass, 1.2 solar masses, there are no dipole suppressed stars there, even though they exist. The normal ones do exist in these lower masses. So this was very interesting, and it says that something is going on that we don't understand for about half of red giants, of these massive red giants. Okay. A companion paper came out that tried to explain this result with what's called the magnetic greenhouse effect. This is an image of what's going on here. Again, we're going to excite a standing wave at the surface. We're going to excite a dipole wave. Okay, it's going to then travel down into the interior of the star. And it turns out that in these red giants, there will be a point at which higher order modes, L equals 1, 2, 3, things that have higher spatial variation on the surface compared to dipole mode won't go further. The dipole mode will go through though, those other modes will be reflected out. And it will continue to travel through. At this juncture, it will cease to become a sound wave. The details are not important. It'll become a gravity wave. That's the same sort of wave that you have in oceans. That gravity wave will then travel down until a certain point at which there's a really strong magnetic field. That's what this kind of green ball in the center is representing, is a strong magnetic field. So the idea here is that if you have a strong enough magnetic field at the center, then this wave can't move the gas in the presence of that strong magnetic field. Because the magnetic field, as I told you before, is kind of coupled to the gas. And if it's strong enough, it's going to be like rigid rods holding the gas in place. So the only thing that mode can do is reflect off of it, so bounce off. And as it does so, it turns out that it will actually scatter into a higher frequency. And those higher frequencies, as I said before, will not make it past that boundary, so they'll be trapped in the inside. They come in, and then they never come out. Okay, so this would predict then that the dipole modes lose energy. As they're excited at the surface, they just never come back out, and so you don't see them at the surface that much. This would predict that the magnetic fields in some of these stars are maybe 10 million times that of the sun at the surface. So huge magnetic fields to produce this effect. To just give you a visual reference, this is sort of like, it's called the magnetic greenhouse effect because it's sort of like the greenhouse effect on the Earth, where you have infrared light coming in and not all of it coming back out, because it gets scattered around. Okay, so this gave us some estimate of the minimum magnetic field in the interior of these red giants. It has to be at least, hundreds of thousands of times the magnetic field at the surface of the sun. But it was only in 2022 that these magnetic fields in the core of giants were detected, again using Kepler, looking very happy. And it goes back to this splitting of modes thing again. So here we have a rotationally splitted mode, okay, split into 3. This is from the de Heuvel's paper, just to give you a reference. But what they saw, instead of things that looked like this for giving the rotation rate of the core, they saw things that looked like this. Okay? So now the splitting is asymmetrical. You have more of a difference between here than between here and here. And it's predicted by theory that if you have the splitting in the presence of a large magnetic field, it will become asymmetric. So this actually, depending on how asymmetric the splitting is, gives you an estimate of the strength of the magnetic field in these cores of giants. And what they found is that these giants, these handful of giants that they studied, got up to 100,000 Gauss in the center of these stars, which is 100,000 times, about 100,000 times, what the sun's magnetic field is at the surface. And that's a bit of a mystery, again, because how does it get those really strong magnetic fields in the center? Turns out that you can have a similar sort of thing as conservation of angular momentum. You can conserve the magnetic field as the core shrinks. It should increase the magnetic field inside the core. But models don't predict this amount of magnetic field. It turns out, again, like the core rotation rate, that the magnetic fields are a little too weak in observation compared to in theory. Just like the rotation rates were predicted to be stronger than they actually were. All right, so that's with Kepler. I just want to end on TESS. So TESS was launched in 6 years ago now. Actually, it celebrated its 6-year launch anniversary on the 18th of April. So happy birthday, TESS. Happy belated birthday. TESS was the follow-up mission to Kepler. And this is a picture from the launch of TESS at Cape Canaveral. I would have been in this photo, but the weather did not work out that day. As people who worked on asteroseismic data, we were invited to come to this launch, but the weather wasn't great for the launch day, and I couldn't stay for, it ended up being several days that it was delayed. So anyway, my friend Jamie Tyre sent me this photo to use to pretend like I was there. So she's here in her red shirt. Thank you, Jamie. So what's so exciting about TESS is that compared to Kepler and K2, it is looking at the whole sky and not just around the ecliptic plane. So this is the view of all the red giants that TESS has found, well, many of them. And you see that they're distributed all across the sky. And when you add their positions, That's the view that we get from TESS. So all of these stars have solar oscillations, and we can get really exciting information from these giants. I'm really looking forward to the next 20 years of high notes, greatest hits from asteroseismology using TESS and future observatories. So with that, I would like to thank you for your time, and I'll take questions. Yes.
About asteroseismology and its application to stellar aging. My understanding is that the waves will change as the amount of helium grows in the core.
That's correct, yes. So as the star ages, it produces more and more helium in the core. That will change the sound speed profile in the core. And because these asteroseismic modes are sensitive to the sound speed profile, they're sensitive to changes in helium composition in the core of these stars. So indeed, you can, if you get good enough data, you can age date a star using asteroseismology, just using the frequencies alone. You don't, as it turns out, have to do that. Go and measure each particular frequency. You can also use general properties about the frequency of a star. So maybe I can go to the solar spectrum that we looked at a little bit ago. So this solar spectrum, as you can see, peaks at a certain frequency that corresponds to about 5 minutes. Okay? But without actually measuring in detail what each of these mode frequencies are, you can just measure kind of where the peak is, which is easier to do. And it turns out that that peak is sensitive to the atmosphere. The frequency of that peak is sensitive to the atmosphere conditions in the star, which turns out to be related to the mass of the star. And if you know the mass of a red giant, at least, you basically know its age. Red giants, if they're more massive, they burned through their hydrogen on the main sequence very quickly. And so then they become a red giant, versus a red giant that's at a lower mass. It had to have spent a long time burning its hydrogen into helium in its core on the main sequence before it became a red giant. So the prediction is that if you know the mass of a red giant, you know how old it is, because the higher mass red giant didn't spend much time on the main sequence, so it is a newly minted red giant, versus a low mass red giant is one that had a long main sequence lifetime, so it must be old. So those are two, broadly speaking, different ways that you can get ages. You can measure the detailed frequencies and look at how they change, in combination with stellar models, of course, to predict what those frequencies should look like for a star that's X amount of gig years old. Or you can use this sort of general information about the global properties. They're called the global properties, global asteroseismic parameters, to get an age that way.
Okay, follow-up question. I'm sorry. Follow-up question. Does it work across the whole range of stars?
Great question.
The stellar classifications?
Good question. It does not, is the short answer. This is an HR diagram. I can't believe that. I think this is the only talk, maybe in my entire academic career, where I've not shown an HR diagram until now. This is called an HR diagram named after Hertzsprung Russell, and what it shows is the temperature of a star on the x-axis, and on the y-axis is the luminosity of the star, how much energy it's outputting per time. Okay? And the main sequence, what the sun is like, is on this black curve here. The giants are in this kind of red, it's called the red giant branch. And then you have all these other regions of the HR diagram. If this HR diagram is colored by some hatched region, it means that they support some sort of oscillation. So it doesn't work everywhere. There's an instability strip where you have quote-unquote classical pulsators that have very large variations in their intensity of light. You can measure their oscillations very easily. You have red giants, which are undergoing quote-unquote solar-like oscillations, which we've been talking about. We've only been talking about solar-like oscillations today. And the main sequence can also exhibit those solar-like oscillations. But you can see that not every part in this diagram is predicted to have oscillations. Okay. Yes.
Plato's coming up in about 2026. You going to be tapping into that project at all?
I will be, but I will not be involved in any of the administration behind the scenes. I will just be benefiting from the data. So that's the European mission that's going to give some high-quality asteroseismic data. And I'm excited for it, but I will not be involved in any way really with it except using the data. So yeah.
If anyone has a question, just let me know. I'll give you the mic, just so everyone can hear your question, because it's facing forward.
Just a curiosity, you showed Gaposchkin's thesis, and she seemed to have the helium and hydrogen abundance inverted. Do you happen to know anything about that?
What I can say is that helium is essentially impossible to measure on the sun, except during in the corona. You can during a solar eclipse. So it's very difficult to get helium measurements, and I'm not sure how she did, to be honest. So yeah, that might be spurious data. I'm not really sure. Oh, a quick follow-up to that. It may be, now that I think about it, that table is not just for, I don't remember the details. It may not just be for the sun in particular, because she looked at a lot of different stars. I'm not sure about the details of that. They have similar abundance profiles, so looking at one table is like looking at the other. But it's easier to measure helium in other stars that are hotter, but not the sun.
Have novas or stars that are expected to supernova soon been studied this way?
With asteroseismology?
Yeah.
That's a good question. So I talked ad nauseum probably about the magnetic fields in the cores of these red giants. The results on the cores of these red giants are important for thinking about supernova because they indicate that you can build up strong magnetic fields in the cores of stars that will then go supernova, for higher mass stars at least. And that is, of course, important for nucleosynthesis in the universe. High mass stars in supernova produce a lot of the heavy elements. In terms of, asteroseismology on a star that will go supernova, there are some seismologists that have looked at Betelgeuse. So any day now, Betelgeuse could go off. Praying that's tomorrow. But yeah, so you can do that. You can also yell it out, or wait for the mic. I won't encourage that. Wait for the mic. I think they're recording the audio.
You said the red giants, their cores have extremely strong magnetic fields, right?
Some of them do, yes.
How do they detect them? And does the polarity change as it reaches the surface?
Okay, good question. The detection is a little bit underwhelming, and you may recall this plot here. Oh, no, not that one. Okay. Yeah. So these modes are, measuring the frequency of certain modes as you see at the surface, and they otherwise would have the same frequency if the core weren't rotating. Okay, that's one thing. But they've been split because it's rotating, but they've been split in an asymmetric way. So this difference between here and here is different than this difference between here and here. And it turns out that theory predicts that magnetic fields, in the presence of a strong magnetic field, you can shift the frequencies in an asymmetric way. So that's how that measurement worked, is the amount of asymmetry is correlated with how strong the magnetic field is. Yeah. And this, in terms of the polarity, this was only sensitive to basically the radial component of the magnetic field. And so it's not giving you an idea exactly about the geometry of the magnetic field because it's only sensitive to one direction of the magnetic field, pointing straight out of the star.
I have a question as well. So granulation is directly correlated to the rate at which the sound waves are emitted, right? Or no?
Yeah. So I didn't talk about this much because it is a little weird. So the granulation. Oh my goodness, where's that picture? Sorry, we're gonna get there. Okay, granulation. There we go. Granulation. Granulation is a thing that is beating on the outside of the star at all sorts of different frequencies. Just like when you blow over a mouthpiece on a flute, you are actually creating pulses at many different frequencies, some of which are supported resonantly and form a standing wave that you then hear depending on what your fingerings are. So some of those, basically the acoustic cavity selects for certain modes that you're putting in that makes these standing wave patterns. With the sun, it only accepts certain frequencies that the granulation is hitting on it with. So it is related to these oscillations in the sense that this is what is causing those pulses of pressure that we saw in in the organ pipe case. But it's actually happening at all frequencies, as it turns out. It's called a red noise spectrum. So there is power at many different frequencies in the granulation spectrum. And I don't think I have a good picture of the spectrum of what granulation looks like. Yeah. What you would see if you actually looked at a real star, this is how the granulation background subtracted off, but you would see like all of these modes are actually sitting on top of a larger line that is going diagonally across here. That's the granulation background. It's just been subtracted off. Yeah. So most of what you see when you look at the surface of the sun is the granulation. And Leighton only saw that 5-minute solar oscillation because he took those differences. And they would line up every 5 minutes. Otherwise, it's just a bunch of noise. If you look at this granulation, wherever it was. Anyway. Yeah, way back there. Anyway, yeah, granulation is at all frequencies, basically. Does that answer your question? Okay.
Did anyone else have a question? If you could just raise your hand. Awesome.
How does the star's magnetic field change in relation to it moving through its evolutionary cycle? Because there's a lot of things in play here.
Yeah.
Yes, if you grow Mars in size, yes, the core can shrink.
Mm-hmm.
But now we're talking about kind of the generalization of it, because we have many different types of stars.
Right. Yeah, so the question is, how does the magnetic field of a star change with time? That is a complicated question. And one thing is we've seen with the cores of red giants, it seems like one thing that can happen when a star becomes a red giant is it will develop a convective core instead of a radiative core. And as we've seen with the sun, that convective envelope is the thing that generates its magnetic field. So one way to generate that high magnetic field that's been observed in those red giants, in the cores of red giants, is you have a convective core that then at a certain point would go away, but it would leave behind its magnetic field. Another thing so that's one way in which how the star's evolution impacts its generation of magnetic field. Another thing to say is that you do have this idea of conservation of magnetic flux. So as if a star shrinks, it will tend to have a more condensed, stronger magnetic field. The converse would also happen if it expands. But the exact details about how magnetic fields change with time is a complicated question, and I'm not an expert in that, so I will leave it at that. Yeah, those are some principles. Yeah. But asteroseismology is good at getting at answering those questions. Yeah. Okay. Any other questions?
Yeah, I have one more. So we were mostly talking about like stars with similar masses to our sun. I guess my question would be, what about like higher mass stars where the convection zone is like further in the star? I'm a little curious about that. Do we know anything about that, or have we looked at anything, or is most of what we know based on what we know from the sun?
Yeah, good question. So stars that are a little higher mass than the sun actually do not have a convective envelope. So they're radiative, where the convective envelope would be in the sun, it'd be radiative. So it doesn't efficiently produce those sorts of solar-like oscillations that are produced from granulation of the surface. It nonetheless will oscillate. It will just oscillate in the core, as it turns out. And you can see those modes as they get to the surface. So you have a different kind of oscillation. You have gravity waves that can insinuate themselves. So I only mentioned gravity waves briefly, but yeah, those are a hot subject of study. Actually, I have a couple of slides on this. So TESS has observed a lot of these hotter, more massive stars, and has come up with some interesting results. So this is a spectrum of a delta Scuti star. So delta Scuti stars are between about 1.5 and 2.5 times the mass of the sun. They lie in the instability strip, and they undergo these oscillations that are not solar-like, but are actually classical pulsations. What you see here is that they do not have a nice little pattern like we saw with the sun. So there's this big gap here, there are some modes here, some modes here, and so it makes it difficult to understand what standing wave corresponds to which frequency. Like, is this a mode that looks like this? Is it a mode that looks like this? Or whatever. And you need to do that sort of identification to understand the interiors of these stars. So that's what makes asteroseismology of delta Scuti stars. In this case, the pulsations are excited from like a heat engine at work that is making the star kind of pulsate. But what TESS saw was something that looks like this. There's a big splashy paper that, because TESS observed thousands of such delta Scuti stars as opposed to a few hundred in Kepler, there were found some regular looking stellar spectra that have kind of a pattern going. Their peaks are separated by kind of a constant amount, and that turns out to be much better to do some modeling of these stars. So yes, you can do asteroseismology with higher mass stars. Yeah.
Any other questions? Okay, well, let's give a round of applause for Dr. Joel Zinn. So we actually have the telescope set up tonight. So if you guys head out to our telescope farm, but also real quick, May 31st will be our last Skylark speaker series for this academic year. And we are going to have Paul Robertson from UCI, and he studies old low-mass stars and looking for habitable zones for exoplanets. So another planetary person. But I will say that sometimes our speakers do surprise us with what they're going to talk about, and they talk about things outside of their typical research. So there's no guarantee that that will be what he talks about. But if you don't follow our newsletter, give our newsletter a follow, and that's the fastest way to know what's all going on in the planetarium. So thank you all for joining us today. And again, maybe we can go check out the beehive cluster outside with the telescopes.